Hello, everyone. Welcome to the Graphics Programming Virtual Meetup. Today, we will talk about PBRT, the book. And last time, we talked about the shape interface for all kinds of shapes. And today, we will just focus on spheres. Spheres are a special case for quadrics, which is surfaces described by quadratic polynomials. They offer a good starting point for introduction ray intersection algorithms. And in conjunction with such transformation, the sphere can also take a form of ellipsoid if we just scale it. And the PBRT also supports cylinders and disks. There are other quadrics such as cones, hyperboloid, and the paraboloid, which are less useful, so PBRT does not include them. Many surfaces can be described in implicit form or parametric form. And implicit form are like this. So it's a 3D, it's a function with a point as input and then a distance. Distance is equal to 0 in this case. So for example, for a unit sphere, we have this. Surfaces can also be described parametrically using a function to map a 2D point to 3D points. In this case, the sphere has a radius and also the 2D spherical coordinates data and what is
Phi?
phi. Yeah.
Yeah, you did the hover over trick. Good thinking.
I just remember that there were two different notations of these spherical coordinates, and it's exactly opposite. So it's need to be careful what kind of notations PBRT use. We can transform this into a FUV over this interval and then just to allow partial spheres that only sweep up a certain area with this substitution. So this form is useful for texture mapping, and that's why we call them U and V, where we can directly map a texture on a plane into the sphere. So left is a partial sphere and right is the whole sphere. And we use both implicit and parametric description of the sphere, depend on which is the most natural way to solve a problem. the sphere class represents a sphere that is centered at the origin, so they don't need to specify a point this way, but just a transformation. So PBRT supports animated transformation matrices, but the transformation here are not animated. And animated shapes are handled by using transformed primitive. I guess the assumption here is that animation is rare. Most primitives does not move, so they just don't want to store it in every primitives. Yes, to centralize some tricky details related to animation in a single place rather than require all the shapes to handle. Radius of a sphere can be arbitrarily positive. Okay, so if we set maximum and minimum z values, then part of sphere below and above those planes will be cut off. Spherical coordinates and maximum phi value can be set. And the section of sphere with spherical phi value above the phi max is also removed. Reversed orientation basically just the normal, which I guess is useful if you say if you want to have an environmental map on a sphere and then the normal you just point inside. That's a lot of data for a sphere. I guess they want to do all those advanced stuff like partial spheres. Yeah, bounding box is just straightforward, just use the radius, but I guess the only difference is that they use the z min and z max because what's below and above get cut off. There is also a normal bound, which does not consider any form of partial sphere. Intersection test, they have basic intersection. Interaction from intersection methods that transform the intersection into full-blown surface interaction. Okay, yeah, so this intersect P methods just want to check whether we have intersection or not, then it does not need to do actual work for lighting. And the second is PBRT's GPU render path is organized such that closest intersection among all shapes is found before the full surface interaction is constructed. This decomposition, yeah. But I guess then for the GPU render, they can't use this function. They need to do something different, I guess. And quadric intersection stores a parameter t along array object space intersection point. And sphere's phi value there. Yeah, we first transform ray origin and directions to the object space, which is stored in those like special kind of class, which also bound the floating point errors. So later, those errors become useful to improving the geometric accuracy for intersection. And then it's just solving the quadratic equation, like a sphere is centered at origin of radius r. We have this, and we substitute in with the ray equation, we get this, and we can expand it into a quadratic equation like this, and with A and B and C calculated. Then we can just solve it by like high school math. But the kind of interesting thing is that they stored an interval class, which stores a small range of floating point values to maintain bounds on floating point rounding errors. Yeah, but otherwise it's just calculating A and B and C, and then doing some high school maths. But we use a variant of traditional approach that gives more accuracy. So they do something different from like the traditional approach to improve accuracy. I guess this is not in this chapter, but in appendix. Just in another section. Oh, T1 and T0 are intervals, so they can overlap. We use their lower bound for this test. And so in the ambiguous case, we do not risk returning a hit that's potentially further away than the actual closest hit. When testing t-value against acceptable range, we also need to test for, in the ambiguous case, we err on the side of returning no intersection. Interesting. I still need to wrap my head around that. Does anyone understand it? Is this?
I'm reading it right now. I'm not sure.
Yeah, I'm not sure. And I don't know how that paragraph corresponded to this code. This code looks pretty standard.
I guess is it that just that first if statement with the because is upper bound the error upper bound?
Yeah, no, yeah, the like arrow upper bound. I guess, yeah, they use upper bound rather than lower bound for this test.
So I guess if because I guess T0 might have been reported as a hit, but if the upper bound of its error is outside of the range, then you don't want to use the hit.
Oh, yeah. Yeah. I see.
The second if statement actually seems redundant. Oh, never mind. Oh, right. Oh, there's T0 upper bound and T1 lower bound. Okay, I see. Right. Okay.
I find it a bit weird though. Like, what if T0 is not a hit, but it's super large, but well, and then T1 is a good hit, but in this case, if T0 is greater than T max, then we just,
Well, it says a case that T1 is always greater than T0 when the way they solve the quadratic equation.
oh, yeah, I guess so. So T1 is at least T1's lower bound should be greater than T0's lower bound, and same for upper bound, but they may overlap with the upper bound and lower bound, but not the other way around. I see. And then we can calculate the intersection point. All the respective interval types cast back into the no interval, which we just use the midpoint. And the refined sphere intersection points will improve the accuracy of this value. And also necessary to handle partial spheres which clip the Z or phi ranges. Just ignore the intersection at those points. By computing the phi value for the hit point using the parametric representation of the sphere. Yeah, tangent. So phi is A10 y over x. And necessary to remap the result of standard libraries A10 function to a value between 0 and 2 pi. Yeah, because A10 returns negative pi to pi, I think. It's a lot of work though. Like this should be slow. And then hit point cannot be tested against minimum and the maximum for Z and phi. It's important to skip the test if the range includes the entire sphere. And yeah, the computed the may be slightly out of the range due to floating point again. So yeah, we only do the test if this is greater than the next, the mean is greater than the negative radius, and same for the max. So it does not cover the whole sphere, and then we test whether the hit is less than those. And we also test phi. At this point, it's certain that we hit a sphere, we create a quadratic intersection. I think this is really because this is interval, then they need to cast it back. Intersection P is just doing basic intersect and ignore the values, just using true or false. And quadratic intersection can be upgraded to a surface intersection by calling intersection with interaction from intersection. First compute the UV value we have phi value and compute data value. Then find the parametric partial derivatives. Partial P, partial U. I'm not sure what those are for, but let's see. U data V partial derivative is just we do the chain rule. And we can substitute it based on the parametric definition of the sphere's y coordinates. So we can substitute the r sine theta sine phi with y. Similarly, like this. This. And here is a bunch of code to implement that. Determine how the normal changes as we move along the surface in UV direction. Okay, so it's useful for AA. The differential change in normal partial and partial U and partial and partial V are given by, I will not try to pronounce that. And I will not try to decipher that. It's just something I don't know. With E, F, and G, which is first fundamental forms. Okay. And second fundamental form. Yeah, we have those partials. We don't have those though. Okay, a little more algebra give us the second partials. I think they should say a little more calculus, or like it's a calculus exercise, not algebra exercise, but whatever. Okay, this is just a code for our calculating those partials, and finally we get those results. This math is something I completely don't understand. I guess, like, also the book does not explain how it works. It's just give us down pass some formulas. So I guess it's fine to just ignore its details. And there are three things to note. The intersection point is provided as, again, as the interval. The surface interaction is initialized by object space geometric quantities. Is transformed to render space when it returns. One of the parameters is the outgoing direction omega. It must be transformed to object space before being passed to the constructor. So that the return interaction omega O value is in rendering space again. Okay. Flip normal. Then the reverse orientation that is enabled, or if the transform swaps coordinate system handiness. That will be that was discussed later earlier, but I don't remember that. And the surface area, I guess, because we need to deal with partial sphere, it's become much more complicated than the whole sphere. The surface area of the resulting sweep surface is from A to B. We have this only partially sweep around an axis, we will instead use this. Yep. Surface of revolution of a circular arc. The function that defines the profile curve along the z-axis of the sphere is yes, and its derivative like this. So we just they should just use the in here, like they use x and then change to the. I thought they will sweep using the like polar coordinates, but instead they sweep with the. So anyway, they do a bunch of stuff and then get this very simple thing. So the surface area is just this. Okay, nice. All the integrals just get rid of, and we have just multiplications. And sampling a sphere area is just sample and then scale. And UV again, we can calculate it from theta and phi. Yeah, and then the PDF is just a constant. But a better approach for a point being illuminated is to sample, is not to sample points on the sphere that are not visible. Yeah, that makes sense. So instead, uniform samples direction over the solid angle. The points lie inside the sphere. The entire sphere should be sampled, so the whole sphere is visible. Yeah. call to this first sample method, give the initial shape sample for a point on the sphere. The direction vector from a reference point to the sample is computed, then normalized. As long as it's non-degenerate, yeah. We compute the value of the PDF value of PDF with respect to the surface area from the call to sample to a PDF with respect to solid angle from the reference point. So it's just a division. Yeah. In the rare case where surface normal and omega are perpendicular, then yeah, we just don't return a sample. For more common case of point outside the sphere, then sampling with the comb proceed. Point is outside the sphere, then as seen from the reference point P, the sphere subtends an angle. Oh, I see. So it's this graph, and we get R divided by wait, P. Okay, I see. So for data max of the comb, we just do some computation, and then I guess this is a special case if it is really small data. For very small data, see you. And for really small data angle, then the cosine square is close to 1. And computing sine square by subtracting this value from 1, then give 0. And accuracy is low. So Yeah, they are less precision closer to 1 than closer to 0. So in this case, we use a single term Taylor expansion near 0. Okay, that makes sense. Given sample angles theta and phi with respect to sample coordinate system computed earlier, we can directly compute the points on, yeah. First step is to find our angle gamma between the vector from the reference point P. Okay, so, and the sampled point on the sphere. And the vector from the center of the sphere to the sampled point. So like this. Applying the laws of sines. So sine gamma is equal to sine theta d divided by, okay, it's sine gamma divided by d is equal to sine theta divided by r. That's law of sines, I'm thinking, and they just put d into this. Yeah, I see. And gamma is an obtuse angle. We can use this. And alpha is this. We can avoid the expensive inverse trig function by taking advantage of the fact we only need sine cosine of alpha. We take cosine of the both sides of the equation. Applying the cosine angle addition formula. And then use two relationships, this and this, we can find that. Okay, there's a lot of steps they just omit in here. But well, I will trust them to get this. And yeah, sine alpha is just this. Yeah, alpha angle and phi gives the spherical coordinates for the sample direction with respect to a coordinate system with the axis centered around vector from the reference point to the sphere center. And phi, what is this? Spherical direction. Oh, I see. It just gives spherical coordinates in a sine, cosine form and a phi, and then it's compute a vector. And brings the transform back to the render space, then we get a normal and point. Yeah, PDF is also differ based on whether we are inside or outside. Yeah, if it's inside, then a uniform area sampling strategy would be used. Intersect ray leaving a reference point in direction omega I with a sphere. Uniform area density of 1 over the sphere area is converted to a solid angle density. Yeah, 1 over area. Value of PDF is easily computed. The same trig identity. I don't know. I don't want to read this anymore. Yeah, it's also worth mentioning numerical accuracy. Yeah, for a small solid angle from the reference point. There we have the same problem. So again, they use Taylor expansion, which is more accurate near zero. All right, this is the whole chapter.